Hey, today we're going to talk about something called the chain rule, which lets you take derivatives of functions of other functions. For example, suppose instead of the usual y, we let a variable u be equal to 5x squared. Then I don't think you would have trouble telling me that the derivative du dx is equal to 10x. And suppose in addition that we have a variable y that's equal to 6 times u, then you could certainly find that the derivative dy du is equal to 6. Where it gets interesting is when we ask ourselves the question, what is dy dx, the derivative of y with respect to the variable x? Well, y is equal to 6 times u, and u is 5x squared, and so y is 6 times 5x squared, or 30x squared. And then we can just take the derivative directly. Dy dx is equal to 60x. Notice that, at least in this particular case, dy dx was equal to dy du, which was 6, times du dx, which was 10x. 6 times 10x, 60x. And it turns out that this is not coincidental and not going to only apply to this one particular example. And why is that the case? Because we're asking ourselves, how is y changing with respect to x? And the answer is, well, it's changing the way y is changing with respect to u times the way u is changing with respect to x. And this little beauty is what we call the chain rule. And the notation is carefully chosen here to make this look like it's intuitively true. It's as if you would cancel the du's on the right-hand side and just get dy dx like we have on the left-hand side. That's not what's going on theoretically, but still the chain rule does hold. Dy dx equal to dy du times du dx. Let's do an example. Let's see if we can find the derivative of this function, f of x equals x cubed plus 5x all squared. If we let u equal x cubed plus 5x and y equal u squared, then the function f of x is y of u. By the chain rule, dy dx is dy du times du dx, and dy du is the derivative of u squared, that's just 2u, and du dx is the derivative of x cubed plus 5x, that's 3x squared plus 5. That's not such a satisfying answer because it's still got a u in it. But we know that u is equal to x cubed plus 5x, and so we can replace the u with x cubed plus 5x to get this expression here. And if you wanted to take the time to simplify or expand or distribute this algebraically, you'd come up with the polynomial 6x to the fifth plus 40x cubed plus 50x. And one reason it's worth doing that is because we can check our answer in this case. We started with f of x equals x cubed plus 5x squared, which if you expand it, you get x to the 6th plus 10x to the 4th plus 25x squared. And now we can just take the derivative like we would with any polynomial, and we get that the derivative is 6x to the 5th plus 40x cubed plus 50x, just like we saw it was when we did it by the chain rule. Okay, I'd like to do the same example a second time, and I'm not really going to change anything except the notation. The notation we just saw I find to be a little bit awkward, and I think that this, once you wrap your brain around it, is a little bit more natural. And in particular, it emphasizes the fact that this is a composition of functions and goes from there. In particular, if you take the two functions, h of x equals x cubed plus 5x, and g of x equals x squared, then f of x, the function we're interested in, is g of h of x. And if you have trouble with that, you think to yourself, well, what's g of 7? It's 7 squared. What's g of 9? It's 9 squared. What's g of q? It's q squared. What's g of x cubed plus 5x? Well, it's x cubed plus 5x all squared. So f of x is g of h of x. And just to remind ourselves, there's notation for that. This is sometimes read as g of h of x or g following h of x, I personally prefer, but you've certainly seen it before. This is function composition we're talking about. And when you look at it this way, what the chain rule says is that the derivative of f is g prime of h of x. In other words, you're treating the h of x as if it were a variable. It was the u in the preceding method of doing this. So we've got g prime of h of x multiplied by the derivative of h of x. To think of it slightly differently, how does this function f change with respect to x? Well, it changes the way that g changes with respect to h multiplied by the way that h changes with respect to x. In other words, we treat the h of x as if it were a variable. Well, g of x is equal to x squared, or g of some variable is equal to the variable squared, and so the derivative is twice that variable, or twice h of x in this case. And then we multiply by the derivative of h of x, which is 3x squared plus 5. I'm still unhappy with it because it has that h of x in the middle, but that is still easy to fix. And we get the same answer that we did before after we replace h of x with x cubed plus 5x. And we really have done nothing different. But the beauty of this second method, once you get used to it, is that we didn't really have to introduce these new functions h and g. We could have started simply with f of x equals x cubed plus 5x squared. And to take the derivative, we would say, all right, we've got some function squared. Well, how do you do that? You treat the function as if it were a variable. In other words, in some bizarre alien alphabet, x cubed plus 5x is the 73rd letter. And so that's just that letter squared. And so what would the derivative, if that were the variable, be? It would be 2 times that variable. And that's the first part. We've got 2 times the function that we are treating like a variable. And then we finish by multiplying by the derivative of that function that we just treated like a variable. And the derivative of x cubed plus 5x is 3x squared plus 5. And here's the chain rule again, stated in what I consider to be a more natural format. It's that the derivative of f of g of x is f prime of g of x times g prime of x. In other words, you treat the g of x as if it were a variable. You treat the function g like a variable, and just take the derivative of the function f, treating the g like a variable. And then to finish, you multiply by the derivative of that function that you just treated like a variable. And for this function that we were just looking at, f of x equals x cubed plus 5x all squared, you didn't really need the chain rule. Not too hard to multiply x cubed plus 5x by itself and then take the derivative of a polynomial. But what if I changed it to the function f of x equals x cubed plus 5x all to the 90th? Well, if you use the chain rule, then the derivative doesn't really get any harder. We have some function to the 90th power. You treat the function as if it were a variable. And if x cubed plus 5x were the variable, the derivative would be 90 times that variable to the 89th power. And now we have to fix it by multiplying by the derivative of the function we just treated like a variable. And that's our answer. Okay. That was the chain rule. There's really nothing more to it except to practice the daylights out of it. I'll do a couple of quick examples for you, give you a couple of examples to try, and then I will set you loose on your homework. Let's start with this function. F of x is the sine of x squared plus 2x plus 3. To take the derivative, well, you know the derivative of the sine of x, the sine of a variable, the sine of x is just the cosine of x, or the derivative of the sine of x is just the cosine of x. You treat this the same way. You treat x squared plus 2x plus 3 as if it were the variable, and so the derivative of the sine of that variable is the cosine of that variable, but you can't stop there. You have to finish the problem by multiplying by the derivative of the function that we just treated like a variable. And so we have to multiply by 2x plus 2. Just in terms of convention, it's nicer to put the 2x plus 2 out in front. That way there's absolutely no confusion about what you're taking the cosine of. I mean, you are taking the cosine only of the x squared plus 2x plus 3 term, and that's what the line before it says, but the line after it makes it very, very clear that it's the 2x plus 2 being multiplied by the cosine of x squared plus 2x plus 3, not the cosine of the whole thing or the whole product. This kind of problem gives people some trouble, but not because the problem itself is difficult, but only because they forget what cosine cubed means, or they are a little bit too lazy to bother rewriting this. And that's the trick. Before you start doing any calculus here, rewrite this function like this. Cosine cubed of x is just notation for cosine of x all cubed. And now we see we've got some function cubed, and so in order to take the derivative, well, we treat that function like a variable, and that gives us we've got 3 times that function squared for the derivative, and then we finish by multiplying by the derivative of the function we just treated like a variable. And the derivative of the cosine of x is the negative sine of x. It would certainly be horrible to leave the negative sign wrapped up inside the multiplication there, and so we bring it out in front and write this as negative 3 times the rest of the stuff, and we may as well rewrite cosine of x all squared as cosine squared x now that we're done doing the calculus. Okay, one more for me, and then it's your turn. Take the function h of x is equal to e to the x squared. And to take the derivative, we treat the x squared as if it were a variable. We know what the derivative of e to some variable is. It's just e to that variable. And so the derivative starts with e to the x squared. And then we multiply by the derivative of the function we just treated like a variable. And the derivative of x squared is 2x. And once again, we can rewrite this in a nicer fashion as 2x times e to the x squared. You certainly want to bring the 2 out in front. It's horribly ugly to leave a constant in the middle of an expression like that. And you may as well bring the x out in front as well, so that it's clear that the e is not raised to anything, except the x squared that we have there. So 2x e to the x squared. Okay, your turn. Try all 4 of these. We will pause in between each one, so if you want to check your work after each one, you can, or you can try all 4 and then start it up if you like. But try them all, and when you're ready, start the video up again. So pause now. For the first one, we treat the 7x as if it were a variable, so the derivative becomes e to the 7x, and then we have to multiply by the derivative of that function we just treated like a variable. And the derivative of 7x is 7. And so we get e to the 7x times 7, or 7e to the 7x. I promise to pause briefly between them, so if you need a moment before you move on to the next one, you can pause now. Otherwise, here we go. Same idea here. We know the derivative of the sine of a variable. This is the sine of a function. You treat that function like it was a variable, and we get that the derivative is the cosine of that function that we're treating like a variable, multiplied by the derivative of the function that we just treated like a variable. And as before, it's nicer to write that as e to the x cosine e to the x, so that it's clear what we're taking the cosine of. Ready for the next one? Okay, I warned you about these problems. Before you do any calculus, rewrite this. Secant squared x is just notation for the secant of x all squared. And so to take the derivative, we treat the secant of x as if it were a variable, and if we had some variable squared, the derivative would be twice that variable to the first, or twice the secant of x. And now we have to multiply by the derivative of that function we just treated like a variable, and the derivative of the secant of x is the secant of x times the tangent of x. Which of course simplifies to 2 secant squared x tangent of x, since secant of x times secant of x is secant squared x. Let's give ourselves a little bit more room for the last one, since I seem to have crowded it out a little bit with the previous problem. Here we go. We've got some function to the 10th power. And so you treat that function, regardless of how complicated it looks, as if it were a variable, and you get 10 times that function all to the 9th power. We are of course not done. We now have to multiply by the derivative of this function that we just treated like a variable. And the derivative of 5x squared plus 3 all to the 3rd minus x to the 4th is the derivative of that first part minus the derivative of that second part. And for the first part, it's a chain rule problem. you have to treat the 5x squared plus 3 as if it were a variable, giving you 3 times that function that we're treating like a variable to the second power, and now you have to multiply by the derivative of that function we just treated like a variable, which is 10x, because the derivative of 5x squared plus 3 is 10x. And then we subtract the derivative of x to the fourth to get minus 4x cubed, and now we have multiplied the entire thing that we started with by the derivative of the entire inner function that we were treating like a variable. There is some simplifying to do. You would never leave 3 times something times 10 times something else just like that. You would certainly have to at least combine the 3 times 10 into a 30, and while you're at it, you may as well move the x in front and write it as 30x times 5x squared plus 3 squared. And in any case, now we're done. This is the derivative of this function. And so what we've seen is sometimes you need to use the chain rule inside a chain rule problem. Gotta love it. Okay, the chain rule represents a giant leap in our ability to take derivatives of all kinds of different functions. Now we can take derivatives of functions, and so they can get much, much more complicated. And this is pretty much the linchpin in our bag of tricks for taking derivatives. I was going to say possibly, but really definitely the most important of our derivative rules. So make sure that you to get lots of practice, wrap your brain around the chain rule. There's a homework. It's got lots of problems on it. We'll do more of them in class. Have some fun. Looking forward to seeing you soon. Bye.